Hello everyone, this is Ketish here. In this video, I'm going to go through the AQA Combined Science for GCSE Physics Paper 2 Higher Tier from 2021. Question number 5 is on the topic of waves. Different parts of the electromagnetic spectrum are used in medical imaging. Figure 8 shows an image of a person's hand taken with an infrared camera. So the way the infrared camera is, where it's lighter, the temperature is higher. So you can see the thumb and the third finger and the small finger, the fourth finger, the index finger is actually where it's very warm. The first finger and the second finger are a bit more cooler. And you can see the blood vessels where the blood is actually flowing is much more warmer. Explain why the infrared camera is able to show that parts of the hand are at different temperatures. The reason it can show that it is at different temperatures is because there's different shades of gray or black or white. So different temperatures emit different intensities of infrared, which are represented on the infrared camera as different shades or colors. Infrared has a range of wavelength from 700 nanometer to 1 millimeter. Which part of the electromagnetic spectrum would have waves with a wavelength of 6.7 times 10 to the power minus 7? Now minus 7 so let's have a look at the electromagnetic spectrum. So if we start with radio waves, radio, then microwave, then infrared, visible light, then UV, then X-ray, and then finally gamma. Now you should remember that the wavelength decreases in this direction. So the frequency, on the other hand, increases. So what have they actually given us? The infrared has a wavelength of 700 nanometers to 1 millimeter. So if that's 1 millimeter, now visible light, which part of the electromagnetic spectrum would have waves with a wavelength of 6.5 times 10 to the power minus 7 meter? Now that could be very close to visible light, because it definitely can't be radio waves, microwaves, right? So it can't be radio waves or microwaves. Can it be infrared? Now that is 700 nanometers is 700 times 10 to the power minus 9 meter. So that's way too small, smaller than what they have given us. So it should be visible light. Figure 9 shows X-rays and gamma rays being used for medical imaging. X-rays in the first picture, gamma rays in the second. To use X-rays for medical imaging, a machine produces a very brief burst of X-rays. To use gamma rays for medical imaging, a radioactive isotope is injected into the patient's blood. The isotope is circulated around the blood around the body in the blood. The isotope emits gamma rays. Compare the potential risks to a patient of using X-rays and gamma rays for medical imaging. Now, both X-rays and gamma rays are ionizing. but gamma is actually much more stronger than X-rays. So in X-rays, the X-ray is actually coming from the device and it's going through the patient to the film in that direction. Whereas in a gamma camera, it's actually being emitted from the body to the outside. Now, because the radioactive isotope is injected into the patient's blood, it's going to be around for a couple of hours, generally less than about 6 hours. So what are the potential risks? Now, they're both ionizing, which means that they can both cause mutation. Gamma is much more stronger than X-ray, so it's much more worse than X-ray. And they both, the potential risk depends on the amount of exposure to these. So your answer, both ionizing radiation, so there is some risk of cancer. The whole body is irradiated by gamma rays, whereas in X-ray, it is taken only for the part of the body where we are actually trying to look through. Exposure time for gamma rays is longer than X-rays. X-rays are produced by colliding high-energy electrons into a metal target. The electrons have high energy because they are accelerated to high speeds. Only a small proportion of the kinetic energy of an electron is converted into an X-ray when it collides with the metal target. An electron is accelerated through a distance of 15 millimeters. The work done on the electron is 1.2 times 10 to the power minus 3 joules. Calculate the force on the electron. Now, the equation that links force, work done, and distance is work done equals force multiplied by the distance. So the force is going to be the work done, which is 1.2 times 10 to the power minus 13 divided by 0.015. Now, why is it 0.015? I divided the 15 millimeter by 1,000 to get 0.015 meter. And that gives me an answer of 8 times 10 to the power minus 12 Newton. 8 times 10 to the power minus 12. The metal target is made from tungsten. Tungsten has the highest melting point of any metal. Explain why tungsten as the metal target enables the X-ray machine to be more powerful. Now, because tungsten has a much more higher melting point, if you use metals like copper, it will melt at a much lower point. That means the metal is not going to produce X-rays. For it to produce X-rays, you need high energy. Some of the energy of the electrons causes heating, therefore increasing the temperature. So using tungsten allows more electrons to be collided per second than any other metal. That brings us to the end of question number 5.